Okay, let's get going. 1 second. Get the chat window up. Okay, starting now. Right, so today, this is the third 10x live stream, and today I'm going to be talking about performance, my favourite subject. So I'm looking forward to this one. I just wanted to say a little bit about why I'm doing these. Obviously, I'm wanting to promote 10x and get it more well known and get more people using it, so I get more feedback. But also, I want to share some of the things I've learned over the years, some tips and tricks and things, and how I do things. So hopefully, people benefit from it as well. So I'm sharing knowledge. So I think that's really important. And there are lots of brilliant coding live streams out there now for people to learn stuff, but maybe not quite so many aimed at the kind of experienced C++ developer. So I kind of assume that most of my audience are experienced C++ developers. So I'm going to talk in that way and go fairly fast on things. Not going to dwell on the details too much because I think most of us know them. But having said that, if you want to ask any questions at all, then please just ask me on the chat, and I'll do my best to keep checking it this time, as I often forget. So sorry about that. So yeah, please bug me if you've got a question. Right. So why am I talking about performance? What sets 10x apart from other editors, I believe, is the performance. For example, I can sorry, let's try again. I can open up 10x, opens instantly. I can open up, say, an Unreal game, shoot game, it's there instantly, and I can start editing it. That's quite unusual. I mean, this is a massive project with millions of lines of code, and there should be no slowdown at all. So I can search for anything. Sorry, doing find file, not find. And it updates as I type, and everything is instant. And there are millions of results, and it's all there as you type. If I can type, I have to put up with my terrible typing. I never learned to touch type. So yeah, everything is instant. That's my goal. Finding references there instantly. Go through files, everything is there instantly. So that's my aim, to have excellent performance with absolutely massive code bases. So obviously, yeah, I'm doing this to share knowledge, but obviously if you have any questions on 10x specifically, then please do ask. So I want this to be interactive so that you can ask questions and ask why I've done things a certain way, or why isn't a certain feature in there, or whatever it is, or just suggestions or feedback or whatever. So I'll try and make some time at the end specifically for that, but do ask me questions throughout. So there are a number of reasons why 10x is fast. One of them is that I use C++, or C with classes, as I like to call it. So that on its own will give you a performance boost over other languages like Java or whatever. The other thing is I write everything myself. Use very few third-party libraries. One of the reasons big code bases are slow is often because you've got hundreds of people working on them. You've got loads of different libraries all interacting, and often the job is just to do what I call plumbing and make library A work with library B, and then you try and make them work together as efficiently as possible. And it's not always ideal, it's not always easy, but as I'm writing everything myself, pretty much, apart from a few libraries I've talked about before, if there's anything that's slow, I can go in there directly and fix it. It's a bit like a car. If you're creating a sort of cheaper end car, you take bits off the shelf and you put them together, and they don't always work correctly together, but you get a car at the end of it that goes long. If you're wanting to create a Formula One car, I imagine you create everything from scratch with millimeter precision engineering, and it's all done so that everything works efficiently with everything else. So it's a whole integrated thing. I don't know why I'm using a car example. I know zero about cars, and I'm not interested in cars. But anyway, it's the idea that everything can be meticulously and carefully crafted. So one of the things is just don't do stupid stuff. Just don't do things that you know will be bad perf. Just have perf in your mind, everything you're writing, and as long as you don't do anything too stupid, it's quite hard to make things slow. So some of the stuff isn't really clever, fancy algorithms or anything. It's just at every stage, not cutting any corners and doing everything right from the start, which isn't always possible in a big team on a big code base. But because I'm on my own, I can just do it as it needs to be done. So attention to memory, and actually what I'm going to talk about today mostly is memory, because I'll talk about that in a minute, but it's probably what I think is one of the most important things if you're interested in performance. And then obviously threading, which I'll talk about a bit. Hi there. I'll talk about a bit, but we'll see if we get to that. I may just stay concentrating on memory. So one of the things that has been said by a few people recently is, well, I think it was Jonathan Blow that said people don't know how fast CPUs are. A lot of people just don't have an idea of how fast a CPU can go if you take away all the limits. And I think it's right. I think because software is so complex, we very rarely reach the limit of what CPU can do. Even if the CPU is running at 100% capacity, it's still not running as fast as it possibly could, because it will be waiting on memory and caches and stuff like that. So that's what I want to talk about today, is making a CPU run as fast as possible. So talking about memory. Caches. So when I go into studios and help make the game run faster, there's a number of things I look at. One is memory, one is threading. They're probably the two main things, but memory and cache optimizations are my favorite sort of optimization. The reason I say that is because often you can get a massive speed up by making only a small change to the code. So it may be changing the way the data is slightly laid out in memory. So it's sort of arrays of structures instead of structures of arrays and things like that, or packing data in, just packing a few things in so it fits in a cache line or something. And you can sometimes get like a 10 times speed up just from doing that, and everyone thinks it's magic. And it's not magic, it's just thinking about memory and thinking about what the CPU is doing and how it's trying to fetch things everywhere at the same time. So let's talk about let's talk about some of my previous experiences. So I remember way back on the PS1 when I first started in the games industry, it had a if I remember correctly, it's very hazy now, but if I remember correctly, it had a scratch memory that was very, very fast. And it was manual, so if you wanted something to go fast, you put it in the scratch memory. It was only a tiny amount, a few tens of K or something. You stick it in the scratch memory and it runs incredibly quickly. So that was my kind of first experience, and it's just burnt it into my head that if you want to get something to run fast, keep it in the cache. It's because I had to sort of manually do it on the old PS1. You had to manually put stuff in this fast memory and make sure it fitted. And you had to do that to get anything to run, even 30 frames a second. So it's something that's always stuck with me, and it's served me really, really well over the years. So I'll just quickly talk about another example. Oops, sorry. No, before we do that, let's talk about data prefetching, hardware data prefetching. It's not something that's talked about a lot, prefetching, what I usually call look ahead. So we probably all know we can do software prefetching with certain CPU commands. You can prefetch data so that it's in the cache by the time you want to use it. What isn't often talked about is hardware prefetching. So if you've got your, say, cache line, if you sequentially access data, so you've got your data up here. If you're sequentially accessing it, the CPU will actually detect that you're sequentially accessing the cache lines and they're pulled in. And if you're consistent about the way you're accessing data, the prefetcher will detect that and make sure the next cache line is pulled in before you touch it, which is really important, because if you have to touch it and then pull it in, obviously you're going to be waiting. If it's already there, you can do your work on this cache line and know that the CPU is pulling in the next cache line, etc. And it's actually pretty clever, because it can work out patterns. So you can say do alternate cache lines, and it will say, oh, he's accessing every alternate cache line, because actually that's quite frequent, where if you've got a load of big structs and you're just accessing one thing and iterating through all these an array of structs, you may well be hitting every second or every third cache line. And the prefetcher will actually, on some CPUs at least, I'm not well up on modern CPUs, but on some at least, it will detect those kind of patterns and say, oh, he's accessing every third cache line. Let's pull those in so that they're ready. And it can even go backwards as well. So if you're accessing memory in reverse, it can say, oh, he's doing it in reverse. I'll put in those cache lines before. And this makes code run really, really fast. If you've got a huge data set and you just want to scan through tens or hundreds of megs of memory, usually just doing a read operation. If you start writing, you kind of blow the cache usually, but if you're just reading, it's very, very fast to do this, as long as your data is laid out sequentially. If it's not, you'll be jumping around memory and there'll be no benefit. So I want to talk about one optimization I did for a company on a garbage collector. And I won't say what game or engine it was because of NDAs and stuff. But the garbage collector had a load of objects with a load of stuff in, and a load of flags, whatever they were, I don't know. And the garbage collector had to kind of do a mark and sweep phase. It wasn't quite like that, but it was basically going through and setting a flag at the first stage on every object, and then the second stage it would go through and find chase references and stuff like that. And the game was doing an awful lot of objects. It had like hundreds of thousands of objects. And even just scanning through all of these objects to do a garbage collect was taking like maybe 100 milliseconds. It was absolutely crazy. And it shouldn't really have taken that long because it wasn't accessing a whole lot of data. But the problem was because all of these objects were allocated on the heap, and they were huge objects, a whole load of other stuff in here. It was just jumping around memory everywhere, so every single object it would be a cache miss. And to have cache misses on hundreds of thousands of objects, it's going to take a long time. And like I said, I think the garbage collector was spiking up to 150 milliseconds at times. And this is while the game is playing, and 150 milliseconds you notice. So what I did was I pulled all these flags out and just put them into an array or separate arrays of etc. And I changed this into an index, so it just had one index into this array, or there were multiple of these arrays. So the object could still change these flags because it needed to occasionally, but when it's doing a garbage collect, it just has to scan through these arrays, and that's just an array of memory, and that might be a few hundred meg, a few tens of meg, let's say. And that was very, very fast. It wasn't quite that simple, and there were multiple stages to the garbage collector, and I had to do that on everything. But I got the garbage collector down from spiking up to 150 milliseconds down to a constant 15 milliseconds. And that was simply just by laying all the data out. It was very interesting because it wasn't until I got rid of the very last cache miss that suddenly it went fast. So the reason for that is if you can have one cache miss, you might as well have 10 cache misses. Because you've already stored the CPU. CPU has just thrown up his hands and said, I'll just wait around and do nothing for a while. So as I was getting rid of these cache misses, I wasn't getting really any benefit until I got rid of the last one, and then suddenly it flew, and it was just incredibly fast. So that's just one example of how fast CPUs can be if you lay out your data correctly. So what I want to talk about is the find. So this find window. So as you can see, it's updating as I type, and it's going through every single file in the entire code base, and there might be sort of thousands of files, tens of thousands of files in the code base. And it's doing that as you type. I want to talk about a little bit how I do that, and that's why I've been talking about it prefetching. Because basically, I think I talked about this in one of the other ones. I kind of store everything as arrays of lines. So I'll store a file essentially as what I call a string array. So I might as well talk about string array first. Let's get rid of these columns. Okay. So instead of doing just an array of string objects where every single string is an object, I use this class, which is much more optimal. Lord SK, how do you measure cache hits, misses? I very rarely do, actually. I usually just do it by eye, as it were. I've kind of got used to looking at code enough to know when it's going to cache miss, and I can just kind of see it. Obviously, there are various profilers and stuff you can use to measure cache misses. And yeah, it's definitely a good thing to do. But if you're working on something like that garbage collector I was talking about, you kind of know when you've done it because it suddenly just flies. And it's also about writing code from the start so that you know it's going to be good memory-wise. Like, I wouldn't do this, store an array of string objects, or if I did, I'd put an allocator behind it so that I know it's all laid out contiguously in memory. So some of it is sort of preemptive, like that. Okay, so going back to string array. So the string array, I don't know, should I make this a little bit bigger? You see, string array has two arrays internally. One is an array of indices, and the other is an array of the actual chars, the string chars. So all of the chars are laid out in memory, and then this is just essentially an array of pointers into these chars. Because often when you're using string arrays, you're not usually doing random access, and you're not usually adding and removing that much. Often I use string arrays just to pass something to a thread or something, so I'll just pre-allocate a string array, so it's this size, copy everything into it, and then use it as a read-only buffer. This class does allow for all those other things if I want to. You can add and remove things wherever you want, so it's just like a normal array. And it has an is optimal bool. So a string array is optimal if all strings are laid out in order and all pointers are laid out in order, and then it's considered optimal. If it gets too unoptimal, then it will actually recreate the whole thing so that it is optimal again. I don't even know if that ever gets hit or if it's probably needed. It's probably not, because I don't usually have that much churn in my string arrays, as I said. And as I free them, I just put them onto a free list so I can just reuse them if I need to. So it's like a normal array of strings with an allocator. And if I want to copy one string array to another, it's literally just a mem copy of these two arrays, pretty much, which is almost instant, which would take an incredibly long time if I had an array of string objects like that. So that string array keeps all lines in memory, so it's just like one big block of memory that I can easily scan through, and it's very cache friendly, obviously. So with the files, so for all the files in a workspace or solution or whatever, again, I want to lay them out in memory like that. So the memory is all contiguous for every file. So as I'm scanning through the file, if you imagine I've got the cache lines underneath, and the files obviously can be any size, but as I'm scanning through these files, the CPU can recognize that I'm hitting each cache line sequentially, and then pull it in with the prefetcher, as I was talking about before. Okay, got a question. Do you use specific sized ints, e.g. int32? I notice you have int in the code here. Do you find that you gain more from the access patterns like the memory structure here over the size of structures? Are you using int16 if there's enough control over such sizes? Yeah, I will pack things in using int16s if I can. I've actually found with 10x I can't do that much packing, and I can't use int16s a lot because 10x has to deal with huge data sets. So I'll have millions of strings in a string table, for example, so I just can't use int16s and things like that. So yeah, I do have int16 type in my code base. So somewhere I should have an int16. Don't know where it's gone. Oh, I actually got it U short. but yeah, usually I'll use ints. I don't actually use size t either, which is twice the size. So I find I don't usually need it. Occasionally I need to go bigger than int, but int is usually enough. So yeah, I hope that's answers your question. Okay, so where was I talking about laying out files in memory? Yeah, so what I actually do with the string array is it has I can give it an allocator. And so what I do is I use an incrementing, well, I call it a block allocator, which is basically just a sort of coalesce heap. So every time you allocate memory, it allocates the next bit of memory sequentially. So that each file has lines, obviously, and as I allocate each file, it goes through the block allocator and makes sure the file is the next thing in memory. And you'd probably be amazed how fast that goes. If I'm just scanning through, like for my search, so scanning through my search, each line in turn saying, does this line have this string in it? That is really fast if your memory is all laid out, as I've said. The other thing I do with this to keep it fast, obviously, is obviously I'm threading it, so I have multiple threads all doing different things. So what I'll do is I'll divide this huge array of files up per CPU. So one CPU will do the first n files, and then the next CPU will do the next n files, etc. So each CPU is also being cache friendly. It's also sequentially scanning through memory. And doing things like this is pretty much as fast as a CPU can go. It's not waiting on memory, hopefully, too much. It's only reading memory, it's not writing memory, and it's only reading that one bit of memory. So I'm not reading other things in between where I'm blowing the cache out. And doing all this using all of the CPUs on all of the code. I mean, for example, like a game with, say, 3 million lines of code might only be let's say, 300 meg of actual source data. So all the text files combined are about 300 meg. 300 meg is not actually that much. I mean, that's a lot of code, 3 million lines of code. But in terms of memory, it's just not that much. And if you have like 16 core machine or something with 32 gig of memory, just load the 300 meg into memory and just scan through the whole thing in like 1 or 2 milliseconds. And obviously I'm trying to hit like 16 milliseconds at least per frame. So 1 or 2 milliseconds is nothing, and it will just update as you type, like that. So I should also say everything is async. So when you type a character, that actually kicks off all of these different threads. They all scan through all of the files looking for testing, and then when they come back, that notifies the main thread again, and it will display the results. So even if it's only 1 or 2 milliseconds, I still don't want it to pause as you type, because sometimes it might be more than that. And if it takes longer, typing should be absolutely instant always. That's my rule. Anything that might take longer than a few milliseconds always is done what I call async, moved off into a separate thread. And it works really well, and it's worked really well for a long time. As I've said before, this search window is what I used to. It's the same code as fast find in Visual Studio. So Visual Studio, my fast find is exactly the same code. I actually ported it in C#. This is all written in C#. The nice thing about writing it in C# was actually that because of the way memory allocations work, if you allocate things sequentially, they will be pretty much guaranteed to be sequential in memory. So you don't actually have to worry about allocators or anything, as long as you load in all the files sequentially and you aren't doing too much else at the time. Probably it'll all be sequential in memory and it'll stay that way. So I think that's what made the C# version just as fast. But obviously in C++, you have to manage the memory yourself because of the way, you probably all know this, but for those who don't know, the way allocators work, you'll probably have a fixed size allocator for 8 bytes, 16, 32, etc. So when you want to allocate 8 bytes, it will go, oh, I want 8 bytes, I'll go to this fixed size allocator. 32 bytes, oh, I'll go to this fixed size allocator. And these will be in totally separate parts of memory. So if you've got a file with lines in it, and one line is 8 characters and another line is 32 characters, you would be allocating all over the place and it wouldn't be contiguous at all. So in C++, you kind of have to manage the memory and do a little bit more work than in C#. But it's not too much work, and you still get the same results. Okay, let me check my notes. Let me know if you've got any more questions. Threading talked about, oh yeah, I'll just mention the lowercase, where is it? As you can see, I've still called it FastFind. I haven't updated the name of it yet. Text Finder. So when I'm doing a find, it's case insensitive, so it doesn't matter what case you do. The way I used to do that was I would store 2 separate copies of the file. One was all lowercase and one was normal case. And then I would just search the lowercase string. I would lowercase the string you're searching for, obviously. That was great and it was fast, but it did use up twice the amount of memory, and especially in Visual Studio, you need to limit the amount of memory you use, and even a few hundred meg of memory in Visual Studio is problematic. So in the end, I changed it to be using a case case map. I'm not going to be able to find it now. Where has it gone? Okay, while my brain takes that, I'll take another question. How do you handle inserting into the W string array? I'm thinking something like make a copy at the end of the allocation, leave the original fragment behind, and then you defrag it eventually. Okay, let's take that. Oops. So this is just an array of pointers. So if you want to insert something at the beginning of this array, it literally will just use a normal array insert and just memcopy or memmove the data. Because this is what when you see array, that's my pod array class. So there are no complex C++ types allowed in this array. So that's just an array of ints, and it will literally just memcopy. And everyone would say, oh, yeah, that's really slow inserting at the beginning of this. Well, if it's only memcopying, say, a meg at most or whatever, that's very, very fast. So that's not a problem. So whenever I add a new string, wherever it goes in the strings array, I'll add it to the end of the chars array if I haven't got any free strings I can use. So the string will go at the end of the chars array, and the pointer will obviously go where it needs to go in the strings. And then, as I said, if you start inserting and deleting from this array, eventually it will kind of fragment and be less optimal. So then you can call an optimize function on it if it doesn't do it automatically. So leave the original fragment behind, then you can defrag it eventually. Yeah, so optimize is essentially defragging it. So you start again and just add all the strings sequentially, and then it's optimal again. So yeah, I think that answers that. Yeah, I was going to talk about the char map thingy. Okay, no problem. Okay, I'm not going to be able to find it, the code I want, so I'll just tell you about it. So you can just use obviously STRI, CMP, the old string. I use all the old string C library classes, and that's okay. But the way I actually do it is I have a lowercase char map pointer. And I'll pass this char map into my find string in string. That's what I call it, but just to keep things simple. And obviously, lowercase char map, as you guess, just converts uppercase to lowercase, or whichever way I did it. I can't remember now. And that actually is significantly quicker, noticeably quicker than doing a kind of conversion on the fly, because internally this will probably use a char map to convert uppercase to lowercase, but it will have to grab that char map every time you call the function. If you pass in this char map to here, the compiler is helping the compiler know what you're doing, so it knows that you're continually using this same char map, and it'll be able to do more optimizations, essentially keep that char map in memory in the cache. So it's very, very fast, because this char map will stay in the cache the whole time. But you have to help the compiler a little bit and the CPU a little bit to make it know that it's going to be reusing this again and again. So I found that was actually really fast, and I didn't actually need to store 2 versions of the file in memory, which is a bit wasteful. The other thing I do, which maybe I'll be able to find the code for this, I'm actually looking, that's because I'm looking in the wrong file entirely. I'm in the text finder. That will be why. Here's the word char map I was talking about. Let's see where I pass it in. Oh no, that's something different. Anyway, the other thing I do is I reduce conditionals in the find. So the scanning of a file is just reading it into memory and storing it in the file cache, which only happens once. The actual find is this one. And I create a job with a load of stuff about the request and what it's looking for. So then I kick off a task, as you see, async, find task, using my string arrays everywhere, nice and fast. I also support wildcard matching, which is a little bit slower, but it's still pretty fast. It's been a while since I've looked at this code, so you have to bear with me. Here we go. So because I have lots of different things, like I can do regular expression, you can do case sensitive, case insensitive, wildcards in it. Then rather than doing the conditionals on every single line that you're doing, am I doing this kind of search, do this way, I've actually duplicated a whole load of code and I do it at the highest level on the file level. So when it says search this file for this string or whatever, at that point it will choose which one to do, and then I've got separate functions. So for example, I'm making expression one, and it does all this stuff, going through all the lines, etc., calling the search function on each line, and that reduces a lot of the conditionals. Because I mean, for example, if you're only searching for testing, you don't even have to use wildcards. You can just do string in string, and you can get rid of a lot of the conditionals you might otherwise need. So that's the other thing when you're trying to make something go fast, is reduce conditionals as much as possible so that the CPU isn't branching, predicting incorrectly and stuff like that. So yeah, they didn't make a huge difference, but it all helps keep it all fast. But mainly, like I said, it was the cache stuff that makes it fast. Okay, got a bit more time left. I'll probably go to 5 o'clock today. But yeah, do keep asking questions if there's anything you want clarification on. I was going to talk about the way I do async. I kind of I've established a pattern of the way I do it now. I talked a little bit about this before, but I thought it might be interesting for you to see how I kind of structure things. I'm just going to write pseudocode just because it's quick. So I have, let's say, I'll have a thread pool in the class. So this is my class. Let's call it the autocomplete class, which I use for autocompleting. And I want to do it asynchronously, so that, because often, like I said before, if you're in a global scope and you might get 60,000 objects back, and you want to filter those based on what the person's typed. And obviously that can take a few milliseconds. And then I'll pass in the value, let's say. So this is adding a task to the thread pool, so it essentially spins up a new thread or uses a previous one if it's got one, which hopefully it usually will. So this creates a function, as I talked about, I think in my first live stream. I've got my own function class, which, oops, if I can type correctly, is essentially like that, whatever it's got in it. So that creates one of those and then passes in value. And this is what the thread pool obviously calls with the value. So then I'll do async stuff, which takes as much time as it needs. And then I have what I call a main thread dispatcher. And so when I'm done, I'll do my task finished. I don't know why I'm doing this in my notepad mode and not in my anyway, so just it's nice and clear because it's big. And obviously I can pass in, any result I want. It's a bit bigger so you can see what's going on. And actually what I would probably do here is I would have lines, and this is all pseudocode, but you get the idea. I would actually pass in, I might have a W string array of, say, you know, I don't know, 60,000, but that's what I remember it was in my test case. That would actually be a member somewhere. Sorry, that would be matches. We'll talk about lines. And because this is being modified in the main thread, I'll actually pass that in. When you say that's crazy, that's like 60,000 strings you're passing around. But whenever you do something async, you've really got to take a copy of the data to work on it asynchronously so that it can be changed on the main thread. So, you know, the odd time I don't care about copying by value these string arrays because, like I said, they're just two arrays. I can memcopy them, and it's pretty fast to copy, memcopy, you know, a reasonable amount of data. And then I might, let's say the results are another string array I've filled in, and I'll pass the results back again by value. Hopefully this one will be a much smaller, so I'm not passing too many strings around. And then what I'll do is I'll have a function list. And let's pass this one by reference. So this main thread dispatcher, I'll typically have one of those for the entire process for 10x, and I'll pass it around to different classes. So actually, these will be references because I'll have one thread pool for everything. Again, I don't like smart pointers, so I just use raw references. The main thread dispatcher is obviously as it sounds. It will just add a function that will get called on the main thread at some point later, maybe the next frame, or hopefully the next frame. So this is typically the way I structure everything. Let's make it a little bit smaller so you can see it all in one go. I'll have the filter function say do this stuff, kicks off a new thread on the thread pool. This is the task that runs on a separate thread, and it's just dealing with stuff that's passed in. So I'm not accessing any other member variables and stuff that could be not thread safe. Or if I do, I make sure I put locks in. And then when I'm done, I'll call my task finished, and that'll get called in the main thread. And then I'll notify anyone who's interested. And anyone who's interested can just do add. Do that, and then that'll get called when it's done. So somewhere I'll do that, and then later on this function will get called and the results will be passed in. And this is kind of the way I structure all of my asynchronous in one way or another. I've also got, instead of the thread pool, I've got a TaskManager. So I could have had a TaskManager here. TaskManager has a thread per CPU and queues up a list of jobs to be done, and so is it worth showing this? No, you know what I mean. It has a thread per CPU, list of jobs, and each thread pulls off jobs as it runs out of things to do, which is good for background stuff like the parsing I talked about last time. But other times you want something to happen right now and not be queued up in the task manager. You don't want it to be a task. You want to say just kick off the thread now and do it now because the user is typing in. I could have done it with a higher priority task, but I just prefer to use thread pool. So yeah, that's that. And I was thinking I might as well just show you Linux. If I can remember where the code is. I think it's in parser name. This is actually the parser library that works out when it can autocomplete. So yeah, that's the actual filter function. See if I can find. My brain is slowing down tonight. Let's work backwards. Okay, so yeah, this shows the kind of thing I was just talking about. So it's actually here we go. So it's the parser database. Has an event. Well, you tell the parser database, give me all the symbols it defines in this scope. When it goes away on another thread, again, doing another async operation, finds all the stuff in that global scope and gives you a whole list of everything. So what I do is I subscribe to that event, autocomplete finished, and then when it's finished, this function gets called. And because this is being called from another thread, because I said it's async, it then has to use main thread dispatcher and put it onto the main thread. Now, I know in C++ you have all sorts of fancy libraries, and the proper C++ way of doing it, using STL and task graphs and continuations and all this stuff, and you can do it all very elegantly in one line. And that's all fine, that's all good. I just prefer doing it this way, because it's what I'm used to, and because it's using all my classes that I've already got. And I just think it's nice and clear, and I keep everything as a separate function rather than using lambdas or anything like that. So when the autocomplete is finished, I just do a bunch of stuff. I add CPP keywords and stuff, which I know will always be there. Then I'll actually kick off another autocomplete task to filter it, because filtering it can take a long time when you've got thousands of objects. So if it's already doing a filter task, which it could be, then I'll just store off what I want to filter for later for when it finishes, and then kick off another one. So if you're typing away and giving it new things all the time, it'll finish the filter it's doing and then work on the most current one, which whatever this is. So this can be overwritten multiple times. And that keeps it nice and fast. So again, this is using my TaskManager. I did actually use TaskManager this time, not thread pool, which I may have to look at. It may be better to use the thread pool. But anyway, because if it's parsing at the time using the task graph, it might just queue it up and be slow. So yeah, I will check that. And it does the task. This is the one that's run on another thread, and it calls this global function to actually filter. One second, I'll get to your question. So this is just a global function. Whenever I can, just a style thing, if I can take something out of the class, I do. So if I've just got a simple function which just takes some inputs and gives an output, it's nice if you can just pull out of the class, I think, and just has fewer dependencies. So you just got this global function. and I'll talk about this in a minute, how it actually filters them, because that's kind of interesting. So when it's filtered it, I'll then make sure the list is unique, which again can take a little bit of time. Ignore that for now, and then it just uses the main thread dispatcher. Say it's finished, this gets called on the main thread, which then I can do all my UI stuff that I need to do, telling us that it's done. So I just tell the main 10x interface to update whatever autocomplete list is currently showing, and that has to be done on the main thread, because that will change UI stuff, and all UI has to pretty much be done on the main thread. So that's just an example of using that structure. I talked about using the thread pool or TaskManager, the dispatcher, and then the notifier. And it's just a really nice pattern, I think, really clear what's going on. And I'll often postfix with main on these to say that this, to be absolutely clear, this is happening on the main thread. So yeah, and I'll use something or other task to show this is a task, which means it's async usually. Right, yeah, I had a question. When would you decide not to pass copies when threading? I tend to find newer programs especially tend to approach threading with anti-threading by adding lots of locks. Any idea how you built up the intuition for it to being an obvious approach? In contrast, you have the reader-writer lock you mentioned on a previous stream. What was in the needs of the parser that made you pick that approach? Yeah, great question. Hope you got that. Did I read it clear enough? Because I know on YouTube you don't see the questions. I'll just read it again and have a think. So when would you decide not to pass copies when threading? Well, if the data is, okay, my typing is much worse. If the data is const and not going to be changed at all, then I could. Occasionally I've used smart pointers and just passed a pointer through so that I'm not copying around the data too much anyway. But usually when you're threading, it's that you're updating, say, an array on one thread. On the main thread, you're updating an array, and on another thread, you're saying, do something with this array. So you really, often you have to take copies of things. I mean, I know I've worked on engines where you kind of, or at least heard about engines where you take almost an entire copy of the entire game state, each frame, so that you can work on that while you're displaying the next frame. So everything is totally copied. And it's really the only way to be sure of doing that. It's the only way to be sure of being safe. Occasionally I will use locking, like you say. So I tend to find newer programs especially tend to approach threading with anti-threading, adding lots of locks. Yeah, I mean, I've seen this before, like, I won't say what the third-party library was, but they threaded their library, which was a very CPU-intensive library, and it was sort of big news, it's now threaded. And it looked pretty much like this. Literally, it was terrible, and that was their threading. What often happens when people do threading is you think, oh, that's easy. I'll just chuck everything onto another thread and then add locks until it's safe. Which is totally the wrong way of going about it. Never do that. But it is a mistake a lot of people make when they're not used to threading. Because what tends to happen is you end up serializing everything. So you put it on lots of threads and it all looks really good. It's like it looks like this at first. Oops. Which is great, but then it crashes everywhere. It crashes, and it's not great. So you say, oh, well, all I need to do is put a few locks in until it stops crashing. And then you end up with this, which is actually just the same as doing that, except now you've just used up a whole load of calls. And the reason is because there's locks everywhere. And you say, oh, I can only access this data, when it's locked, and you end up just serializing it over multiple calls. So now you've just got one thread jumping around multiple cores, and it's actually no faster. Or I've even seen it be slower than just doing it on one thread. I actually turned off the threading on one of these libraries, and it was actually faster because locks take time, and you're blowing out caches left, right, and center by jumping around the cores. So locks need to be avoided wherever possible, and taking copies of data when you're threading is a really good way to avoid locks if you can afford the mem copying the data. Did I answer the first question? Let me just go back to that. And you asked, in contrast, you have a read-write lock you mentioned on a previous stream. Yeah, that was for the parser. What was it made you pick that approach? The parser was slightly different because it's mostly read-only with only occasional writes. And the data was so complex and so large that I couldn't take a whole copy of anything. I couldn't just, because as you know, 10x for something like a big Unreal game can take like 10 gig of memory at the moment, which I will be reducing, don't worry about that. So obviously I can't take a copy of sort of 10 gig of memory and say, this thread, go away and do this, while the main thread is, because 10x is parsing the data while you're typing away, and hopefully autocomplete is still working while you're doing that. So it's parsing away in the background when you first load up the project for the first time, and you're typing and it's doing autocomplete, and you're editing the file and it's updating the parser for that file you're editing. So it's a very, very complex scenario. But as I said, most of the data is read-only. So when it's parsing through all the thousands of files, megabytes of data, it's mostly just reading stuff and then occasionally saying, oh, I've got this symbol, this is a symbol, stick that into a map or something, which is very quick. So you just put a small lock around that add to map. So when it finds a symbol, adds it to the map, just lock around that add to map, and then carry on parsing. And so it doesn't actually need locks, it doesn't hold locks for any length of time. That's the key. If you're going to use locks, it has to be absolutely, whatever. So if I'm going to add a lock, it will literally just be around that. I usually use this symbol lock. So it's holding it for a very short time, hopefully. And as I said, the parser is different because it's mostly when it's full on parsing everything, it's literally just doing loads and loads and loads of reading of it. And it's only if I'm actually editing a file at the time, that's the only time it actually writes to the lines and updates the lines and validates a whole load of stuff. So I can put a shared read-write lock, so I can have multiple threads all reading data at the same time. And then the occasional time where I edit a file, then I can take a write lock and lock all the other threads out, because that's quite a rare operation in terms of the parsing at least. So I can be guaranteed that as I'm editing the file, nothing else all the other threads is just locked out at the time, and it's safe. And obviously that's slow for all the other threads, but they're background threads. You don't care if they're all stored when you're editing the file. But the key is having the shared read lock is really, really important, because it means all those threads. So if that's a shared read lock, it means that multiple threads can come in here and well, I wouldn't do that with symbols. That's a really bad example. But anyway, whatever I'm doing, if I'm scanning through the lines and doing stuff, then I can have a shared read lock and multiple threads can be doing that on the same file because they're all looking for symbols and stuff and cross-referencing everything. So that's the reason I use the shared read lock there. And as I said, I had to make it recursive, which is a whole other story. So, similar question. How do you decide when to split something into chunks that you can process with your thread pool? Do you aim for a certain level of single-threaded performance first, a certain amount of full clock time based on the thread pool overhead? How easy, difficult the problem is to split across threads? How do I decide to split something into chunks? Well, I mean, it's done on a case-by-case basis, really. As I said, the search thing was pretty obvious because you've got a few thousand files and you've got 8 threads or whatever, 8 cores. You just split it per core, and it's a kind of no-brainer. In game engines, it's often a lot more difficult, and it is a problem you have to think about in game engines because you often have. I mean, I've seen game engines where you have tasks that are so small that the overhead of actually kicking off the task and adding it to the task graph, whatever it is, and then spinning up the task and then doing whatever it is when the task is finished. I've seen engines where that overhead totally dwarfs the amount of time you're taking on the task. So I tend to try and avoid very small tasks where possible because the overhead just isn't worth it. So I'll usually only split something into tasks if I can have nice big tasks, like I was saying, like this one. You know, if you've got nice big tasks to do, and they can all be done totally independently without locking. Because if you have locks in these tasks, then you're asking for trouble, really. Obviously, sometimes you have to, but you can end up if these tasks have to have locks in them, you end up just doing this kind of thing and serializing it across lots of cores. So the requirements for splitting a task up is that A, the tasks have to be big enough, and B, you have to try and avoid locks wherever possible. So the find thing is the perfect example of splitting stuff across cores in a task manager. It's just ideal. But obviously, in more complex engines and game engines, it does get more complicated. Anyway, I hope that answers your question. So I was using 10x for some in-depth UE4 engine stuff this week, tracking down a problem. I have 2 gig RAM per CPU core, which is enough UE4 to compile. Found 10x memory paged out quite well. Yeah, I was mostly able to keep using navigation while compiling with minimal hit. That's really good to know, yeah, because I mean, 2 gig per core, well, you don't see how many cores you've got, but that's not a huge amount. I mean, working on Unreal, you probably need 1632 gig at least, I'd say, total. But if you're finding it's okay for the engine, then that's all right. Yeah, I will stop in a minute, but I'll talk briefly about my thoughts on the memory usage of 10x, because at the moment it is far too much, and it is all down to the parser. And I've realised that I can actually, like you say there, the questioner said that it did page out very well, and it will, because most of the memory that 10x is using for the parser is never actually touched. Once it's parsed, it just sits in memory, and you probably won't touch it again. Because, and if I can quickly show you, hopefully you saw my last live stream about the parser, so I won't go over that again. So I've got an array of lines, an array of parse thread lines in this case, and as I said before, has the line text, and then an array of tokens, and it's storing this line for every file in the code base, and it really doesn't need to, because I have a central database for the parser, which does have a hierarchical map of all the symbols that it needs. So if you want to look up references or something, it has one single centralized database for that. And the only real reason I think I need to keep all this token data in memory is for when you open a file and you want to see the syntax highlighting and go to definition. But for really huge code bases, you're probably only working on like 5 or 10% of the code base in general. You're not opening up 10,000 files and editing them all. So that's the reason I think it pages out quite well, because most of the data, once it's loaded in, isn't touched again. But obviously, it'd be nicer if that overhead wasn't there for 10x. So I'm actually going to do manual paging, where I page out these lines, I dump them out to file, or at least don't read them in the first place. Once I've parsed the entire database, as I'm parsing, I'll dump them out to the file, so it's not sitting around in memory. And then as you open a file, I'll just quickly stream in the lines that you need so that you get the syntax highlighting and go to definition and references and stuff. And I think that'll be fast enough. You might see a one frame glitch or something as the syntax highlighting comes in, but I'll remember the files you open frequently and have those in memory the whole time. So I'm hoping once I do that, the memory will go down drastically. I'm still thinking about it in my head to make sure that there's no other dependencies that might need that data. But fingers crossed, I'll be able to reduce the memory by quite a lot. But as you say, at the moment it pages out quite well. So I'm not too worried at the moment, but it's definitely on the cards to do. So this question saying it does answer quite well. Okay, my answer, I guess, to the threading question, thread pool, sorry, task graph, TaskManager. It depends being the answer, yeah. So I find examples like search really useful, as every time I can pass on a circumstance where when approach applied well can help people towards building up that intuition. Yeah, so it's really good to know the good cases. I mean, you don't often find a case as good as the search example I showed. That's like the perfect example. And that's actually why I did it, because I was totally fed up with slow searches in editors when I was using Visual Studio, and I just thought, how fast could a CPU go if I had perfect threading and perfect memory access and just read-only accesses? How fast could I churn through 300 meg of memory? I'm sure I could do that in a millisecond or two, and it turned out I was right. So it really is the perfect example. Nothing's ever that simple usually in life, or in game engines at least, and it's usually a lot more messy and usually involves locks and stuff like that. But it's nice to know the perfect case, which is why I thought it'd be interesting to talk about today. But yeah, it is about finding an intuition on these things and knowing what's going to work well and what isn't. So a lot of people just dive into threading, like I said before, and just end up adding more and more locks until it stops crashing, and then they think they're done. But if you actually profile the code, you haven't actually made any improvement because you've just serialized it across the cores. So it's something you have to keep on and on checking in profilers such as FramePro. You have to keep checking to say, am I still serializing? Obviously without any crashes. Am I still running like this? And when 10x parses all the files, you can actually look in TaskManager and see all CPUs being used at probably 70 or 80%. The reason it's not 100% is because I always keep one core free, or at least the equivalent of one core free, so that it doesn't totally lock up your system. Because I've noticed that Windows recently, it does lock up, especially with input, if you use up all cores to 100%. So I'm sure I never used to do that. Yeah, or worse, assume lock-free makes it just work fast. Yeah, be very skeptical of lock-free. I can do another talk about that sometime if you want. I spent far too long working on lock-free algorithms, and they're not always faster. Let's just say that, as the questioner obviously knows. So yeah, trying to avoid locks wherever possible. And the main theme of this talk is lay out your data well. CPUs are incredibly fast these days. And you can just really make them fly if you really lay out your data well. And it's much easier to do that up front than it is to retrofit that. So yeah, it's definitely worth giving it a bit of thought before you jump into it. Okay, I think that's everything on my list I was going to talk about. Questionnaire. So use your brain. You know the memory and threading opportunities the system compiler doesn't. Exactly. Yes. Help out the system and compiler as much as you possibly can. You know, assume it's really stupid. Yeah. So I think we'll leave it there today. Thank you for watching. Again, as I usually say, do let me know if there's anything you want me to talk about specifically relating to 10x or my code. I'm totally happy to share anything, pretty much anything. So you just have to let me know what you want to see and what questions you've got. So yeah, do carry on using 10x, I hope, giving me feedback, and I've had some really good feedback last week or two. It's really kept me busy, which is great. And keep an eye on the versions I post out. This week's I posted yesterday, had a lot of really useful fixes that people have been requesting. So it's those, what I want to know is those useful fixes, because I mean, I've got a million things I know need to be done on 10x. What I want to know is the things that, if you're using 10x, I know how it is, you use it for a while, and then you hit something which doesn't work as you expect, or is missing a feature or something, and then you go back to your old editor, which is fine, I know that happens. I want to know what the things that cause you to put 10x down and go back to your old editor. Those are the things I really want to get fixed straight away, so that more and more people can start using 10x as their main editor. And the reason I want to do that is because it helps me prioritize things that I know people will find useful, because I don't want to be spending loads of time on things that people aren't shouting for right now. They all need to be done, and I need to do them all to make 10x a proper product that I can hopefully sell one day. But at the moment, my goal is to keep all of you users happy. So yeah, do let me know what you want me to look at, and enjoy using 10x. And yeah, happy coding. So I think I'll leave it there. Thanks a lot.